So last week we started talking about normal distributions. We started off with that 68, 95, 99, 7 rule. So we said when we have a normal distribution, every single normal distribution follows that empirical rule. And we said that if we were 1 standard deviation within the mean, we capture 68% of the observations, 2 standard deviations captures 95%, and so on. So we talked about how to use those general percentages to approximate areas under the curve for different ranges of values. Like when I hit those special cutoffs, we could approximate percentages based on that shortcut. Okay, so that's really what the empirical rule is. It's a shortcut to calculating area. Okay, but we said in the real world, more often than not, we're going to be interested in values that don't hit those exact cutoffs. We're not going to be exactly 1 or 2 standard deviations above or below the mean. So in those instances, when we're moving to a different location on that x-axis, how do we then take that and create or calculate that area for that particular region? So we said, how do we calculate the area? How do we calculate the percentages using values that don't fall on those exact cutoffs? So that's where that table A and the calculator came into play. So we're going to be using table A again today. We're going to be using our calculators again. But this time, we're going to be going in the other direction. So last week, given a normal distribution, it was, here's the value in question, what percent of observations fall above, below, or in between. So it was, here's the value, what's the percentage, what's the area associated with that. Now we're going to go the opposite direction. So now we're going to say if we're interested in a certain percentage. So I want to capture this percent of my observations. I want to capture this percent of my population. How do we convert that back to a value? Okay. So what's going to happen here, we're going to follow essentially the same steps, but just in reverse order. So when I want to find values based on percentages, I'm going to start with my table. And I'm going to find the appropriate percentage for the cutoff score that I'm looking for. But that cutoff score is going to be in standardized units. When I look it up on the table, I'm going to be getting a z-score. So that would tell me what the standardized value for that percentage is, but I want to take that standardized value and I want to convert it back to an actual value for my context. So last week it was, here's the value, calculate the z-score, look it up on table A and get the percentage. Now we're just doing all of that in reverse. We have the percentage, so we're going to use it to find the z-score. Use our z-score formula to work back to a value, and then interpret that value in the context of the problem. So the pieces are all going to be the same. We're still going to have the z-scores. We're still going to be sketching our normal distribution. We're still going to be interpreting in the context. It's just the direction that we're heading is going to be opposite. So since we've already talked about most of the processes involved in these normal distributions, we're just going to jump straight into an example today. So if I give you the example, scores on the SAT verbal test in recent years follow approximately a normal distribution, mean of 505, standard deviation of 110. How high must a student score to place in the top 10% of all students taking the SAT? So last week it would have been a student scored, or in order for them to be in the top 10% or whatever, it was like, here's the value they need. What does that value look like in terms of percentages and stuff like that? So it's, here's the value, what is the percentage associated with it? Now we're saying we want to be within a certain percent, what value do we need to obtain that? So in this case, the other thing that's important to note here, when we're using table A can only tell us which direction. Left. Table A only knows how to work with areas to the left of a given point. So if I'm looking for the top 10% of all students, that means I'm looking at 10% to the right. So that's why in this statement down below here, we're saying that if I'm doing top 10%, I need to be thinking about 90% to the left of the cutoff point I'm interested in. So the standardized value that I want needs to have 90% to the left because that's the value, that's the argument that the table can take. So what you're going to do then is once you've established what percent exactly you want, top 10% means I'm going to look for 90% to the left. So I'm going to convert that to a decimal. And we're going to look for this decimal in table A. So because it's a large, it's above 50%, that means it's going to be on the positive side. So anything above 50% is on the positive side of table A. Anything less than 50% is going to be on the negative side. So you're going to flip to the positive side of your table. You're going to try to find the percentage. You're going to try to find the decimal that's the closest to 0.9000 as you can. So everybody take a second, try to find the decimal that's the closest to 0.9000 as we can find. So as you look for the table, or look through the table there, you're looking at all the different proportions. The two that you should have come across, the two that are the closest, are this 0.8997 and this 0.9015. So you're always going to come to two spots. So there's going to be two spots, one above, one below. You've got to pick whichever one is the closest to what we're looking for. So out of the 0.8997 and the 0.9015, which one's the actual closest to 90% exactly? The 8997. So this is the value that I'm interested in. So once I find that value, that's the closest percentage that I'm looking for, I follow it up to the top margin. There's the hundredths place of my z-score. I follow it out to the left column. And there's the start of my z-score. So I'm going to find whatever z-score is associated with that specific percentage. So in this case, we get a z-score of 1.28. Now, something to note here. When you're working with these percentages and you're working with table A, so we said it was top 10%. Table can't handle top percentages, so we had to convert to the lower percent, in this case 90. But if I don't want to have to worry about trying to do that conversion, I can also use the symmetry of my distribution to help me out here. So if I'm thinking about the perfect symmetry of this normal distribution, if I'm looking for a cutoff spot up here that gives me the top 10%, right? Then there has to be a corresponding value on the opposite side that would give me the same z-score, but for the bottom 10%. So if I didn't want to have to think about, like I just want to be able to take the percentage they give me and look it up on the table directly, if I were to look up 10% on the table, so everybody look for 10% on your table real quick. So you're looking for 0.1000. So this one's less than 50%. It's got to be on the negative side. So when we looked up the 90%, that's the true percentage we were looking for. We got a z-score of 1.28. When you look up 10%, what do you get? Negative 1.28. Okay, so if I use the symmetry of my normal distribution, I can get my values that way too. So like I said, if it's confusing to think about, top 10 means bottom 90. Like if that conversion just doesn't make sense to you, okay, you can look up the 10% that they're asking about. But if you do look up 10%, what you have to account for is that's going to be the bottom 10%. So the cutoff score that you find is going to be the negative version of what you want on the other side. So I could just look up 10%, I get the negative z-score, make it positive, that's the same cutoff score that I would be looking for on the other side. Is everybody with me on that? So whichever process makes more sense to you, okay, I can either look up the percentage directly and then do my conversion, or I can convert first and then look it up. Either way, you should get to the same answer. Okay, but that's how we're going to be doing that using the table. Whatever percent I'm interested in, I find that in the table. I look for what z-score is associated with that, and then we'd use that to calculate. We're going to do that here in a second for that particular problem. Now, that's how we use the table. If I want to use my calculator, so if the table's not the version you want to use, if you want to use the calculator instead, okay, on the calculator when I want to find or use my normal distribution, what were the two buttons we had to hit to begin with? Second, vars. So I'm going to hit second vars on my calculator. That vars key was right by the arrows. Now when it takes me into the calculator, into that menu, right, option 1 was normal PDF. Option 2 was normal CDF. And option 3 is inverse norm. Okay, now we talked last week, which one of these do we ignore? Which one will we never ever use? The PDF. So we ignore this one entirely. We're never ever going to use the PDF, right? So last week it was normal CDF. This was I had a value. This is going to convert it to a percentage. Okay, so this was the process we talked about last Friday. What I want to do is work the other way. So that's where this inverse norm is going to come into play here. So when you go into that inverse norm function, when you choose that option 3, okay, for most of you, just kind of looking at the calculators being utilized here, for most of you, you should get a screen that looks like this. So it's going to say area, mu is 0, standard deviation is 1, and then it asks for what tail that you want in the distribution. Okay? If you do not have this bottom option, so if you don't have the tail option here, you're just going to have to do the same thing that we just did on the table, where you're either going to have to type in the percentage you want and then convert it, or convert to the correct percentage and then go from there. So like I said, if I was doing this problem, if I want top 10%, I would put 0.9000 in for area, mean of 0, standard deviation of 1, hit paste and enter. But if I do have this option, you have a little bit of an advantage here. Because on the calculator, whereas the table can't do anything to the right, the calculator can. So if I were looking at trying to plug this into the calculator, I can make it really easy on myself because it says top 10%. So I'm going to type in 10% for my area. So 0.1000. I'm going to leave the mean and standard deviation as they are, 0 and 1. And I want it to go to the right. So I'm going to select that option. And then it's going to calculate the area to the right for you, where we wouldn't be able to do that on the calculator or on the table directly. And so then you hit paste, you copy down what you see on your screen, and then you give me the answer, which in this case would be the 1.28. So either way, you get to the same z-score. So whether it makes more sense to use the table or use the calculator, just make sure you're showing me what process you're using there. Everyone okay with converting from the percentage to the z-score? And you'll get some more practice with this on the homework today, but that's the process we're going to utilize. So either using the table or using the calculator, that's what you're going to do. So now to finish this out, if I do take that z-score that we calculated, we need to unstandardize it. So I get a z-score of 1.28. Now we always provide a sketch, so don't forget to sketch your graph. So we create our normal distribution, 0, 1, 2, and 3 to the right, -1, -2, -3 to the left. And then this time when I use my z-score formula, I have the z-score. I plug the 1.28 in for z, 505 in for the mean, 110 in for the standard deviation. And then we just multiply the 110, add the 505, and we get our cutoff score. So a student must score at least a 645.8 to be in the highest 10% of all scores. So the hardest part of this whole process is going to be that first step, figuring out what percentage I need to be working with, what percentage I need to be finding on the table or plugging into the calculator, taking that percentage and converting it to a z-score. Once I get to the z-score, it's just a matter of providing a quick sketch, plugging the value into my formula, and then just solving for x, and then interpreting. Okay, so that's what that's going to look like. Now, if this had been something where we wanted to know how low a student scores to be in the bottom 20%, let's say. So if I wanted to be in the bottom 20%, or they said, what's the 20th percentile for this distribution? That percentage, anytime I'm talking percentiles, that is exactly what the table can tell me. So I can take that percentage and I can go directly to the table. I look for 20%. Whatever z-score I get there, that's the value I want. Plug it in, solve for x, and then interpret. So these top 10, top 5, top 20% problems, those are the ones you have to do a little bit of thinking, a little bit of converting to get to the correct z-score. Anything about percentile, lower percentages, anything like that, it's going to be directly from the table. The other thing then you need to be aware of is what happens when they look for middle percentages. So same scenario. Normal distribution, 505 for the mean, 110 for the standard deviation, but this time we want to calculate the IQR. So if I want to calculate the IQR for SAT scores, we need to remember from our conversation with IQR, that means the middle 50% of SAT scores. So now I'm looking for the middle 50%. If I think about what that IQR entails, it's quartile 1 and quartile 3. So I need to think of those in terms of percentiles. I need percentages that I can use to convert to actual scores. So quartile 1 represented the 25th percentile. Quartile 3 represented the 75th percentile. I do not need to look both values up. I can use the symmetry of my distribution to figure out what these are. So for instance, I can look up 0.2500, or I can look up 0.7500. What's going to happen is the 0.7500 is going to give me the positive z-score. The 25 is going to give me the negative equivalent. So all I got to do is pick one of the two percentages, look it up on the table, or plug it into my calculator. Whatever z-score I get for the one, change the sign. It's automatically the z-score for the other. Okay. So I would pick either of the two, or if I want to look them both up, you can. But when you look up 25% or 75%, you would get z-scores of plus or minus 0.67. So the standardized values, that would represent the middle 50%. So now we use those to unstandardize and get the actual scores. So then it's a matter of plugging the z-scores in, multiplying by the 110, adding the 505. Now when I get my quartiles, because that's what I'm calculating, so my quartile 1, 431.3, quartile 3, 578.7. This is one where I have to think about the context a little bit more. For SAT scores, they don't give decimal points, so they're whole number values. So when I go to convert this to the actual IQR, I need to account for that by giving whole number values. Now notice, when I go to calculate my IQR here, the 579, so the 578.7 got rounded up to 579, which normally wouldn't be that big of a deal because my normal rounding rules would have told me to do that anyway, right? So the 0.7 would have told me round up to the nearest whole number. But notice what happened here. 431.3 became 432. Now, conventional rounding wouldn't call for that. Why do we have to, though, round up in this particular instance? When I calculate quartile 1, what does that represent in terms of the distribution? What percentile? The 25th percentile, right? That means I need to capture at least 25% of my observations. Now, if I were to take the 431.3 and round down, rounding down does not guarantee I'm going to get the full 25% that I need. Okay? So even though my normal rounding rules would say round down to 431, I need to make sure I capture at least 25% for that percentile. So I need to round up to make sure I get as many values as I need to get that 25th percentile, which is why we round it to 432. And for that matter, even though my conventional rules said to round up here, I would have to round up anyway, because again, I have to capture at least 75% of my data on the top end. So I need to make sure I round up to capture at least that 75%. So that's another thing you want to just be aware of. We're not always going to use standard rounding rules when we're making these decimals become whole numbers. Okay? So then this is going to be the assignment.